Hi, I'm Mark Weitzman, and this is a video tutorial on Lorentz transformations and special relativity. And so this is part of my version 2 of quantum field theory, a student's perspective. So let me start by saying that I'm using a lot of new equipment and software here, like right out of the box, that I barely know how to use. My iPad Pro from Apple finally arrived. I'm using some OBS open source software suggested to me by a gentleman named Martin. Thank you very much. And I am using the Notes Plus app. And so combined with all the new hardware software, add to that my terrible handwriting, we'll probably get something that doesn't work that well. But I need to know how it compares to my whiteboard videos and my videos on paper using an over-the-camera camera. So really appreciate any feedback I can get. In the lesson video on Lorentz transformations and special relativity for Chapter 2 in Mark Szugnicki's Quantum Field Theory textbook, I started sort of at the same level that he's using, which is graduate level, and so it assumes a pretty advanced undergraduate understanding of special relativity that some here may not have. And I can only suggest that you try and read up some books and learn some ins and outs of special relativity. We won't use all of them in this course, but I'm going to today do some stuff which you may encounter and everything. So I want to do two things today. One on the rapidity or hyperbolic parameter, and the other on uniformly accelerated motion. Now I'm going to try and do these in a fairly elementary way. And so let's start. One of the references that I have for this is I'm going to display it. Rindler's book on relativity, special, general, and cosmology, 2nd edition. Special, general. So this is an old-fashioned book. It doesn't have like all the modern notation and everything, but because of that, it has a lot of interesting things that you don't find in some of the new books. Things like how things actually appear in special relativity, or uniformly accelerated rod. I wrote a paper that's on my Piazza website, and you can see the link to it on the YouTube video. When it says more, there'll be a link to my Piazza website. So this is sort of an old-fashioned book that covers a lot of things that just aren't that important by themselves, but they add up. And so I recommend the book. And it's not difficult at all. So in kindergarten, we learned the equations for a boost in special relativity. And so let me write down those equations. T prime equal gamma T minus Vx. Gamma is equal to 1 square root of 1 minus V squared. Remember, C is always equal to 1 in this course. And x prime is equal to gamma x minus Vt. And y prime equal y. Z prime equal to Z. So Y and Z just always go along for the ride. Now, I used a phrase in kindergarten. Why did I use that phrase? Well, that's a phrase that Steven Weinberg used quite often in his textbooks. You know, he'd be doing some really advanced thing in quantum field theory, and he'd go, in kindergarten we learned this, but now we're going to do it in a more sophisticated way, and so on. Steven Weinberg passed away about a week ago. He was 88, and he was probably, I rank him just below Feynman. I mean, he was probably the premier physicist of the Standard Model. He developed a lot of things, and he always worked by himself, and he published tremendous textbooks, and he really contributed to both education and to physics, and a lot of other things. He wrote a lot of essays on a lot of different things. So I highly recommend reading all his works. So these are the equations of special relativity. It's really just these two. And it's amazing how much you can get just from those two equations, along with, I guess, this. Now, why do we need a rapidity parameter? It seems we already have a parameter, which is basically V is sufficient. And for most purposes it is, but there is an advantage of at least being familiar with the notation, and sometimes the rapidity parameter or the hyperbolic parameter comes in handy. So to start, to motivate it, if you recall, okay, recall for a rotation, let's say we have x, y, and we rotate by an angle theta. So this becomes x prime and y prime. And so theta is the parameter for a rotation, and just to write down the equations, x prime is x cosine theta plus y sine theta, y prime equal minus x sine theta plus y cosine theta. All the books use different versions for the signs here. It depends whether you're using an active or a passive transformation, but I think I got the signs right for a passive transformation for rotating the axes. So it's easy to show that theta is an additive parameter. So what does that mean? That means that if we do like a rotation by theta 1 followed by a rotation by theta 2, that's the same as, remember, we're rotating about fixed z-axis. So those rotations commute, and so this is equal to r theta 1, r theta 2 is equal to r of theta 1 plus theta 2. So the angles are additive. And as a matter of fact, if you substitute imaginary angles in these formulas, you'll end up getting the our old friend, the Lorentz transformation. But and while this was sometimes done maybe 50 or 60 years ago in some books, you know, they keep the geometry Euclidean and they use imaginary time. That really doesn't work, especially when you do quantum mechanics. So we don't want to do that. We want to keep a Minkowski metric and real coordinates. So what we want is we want to do the same for this for boost. Now, when we have a boost in the same direction, we have that like B of V2, B of V1 equals B of V1, B of V2, but it's not equal to B of V1 plus V2. As a matter of fact, it is equal to B of V1 plus V2 over 1 plus V1 V2. And if you remember, this is the formula for velocity addition. In special relativity. So we want to use a parameter where it will work. So let's try and find that parameter. Now, there's two ways, well, there's probably many ways to do this. One is to go directly from the large and sort of do it as Rindler does it. I'm going to follow Rindler in this video. But Chernecki does it also in problem 2.9d. So he does it from the infinitesimal, a little more sophisticated way of doing it. But I'm going to follow Rindler. Now, the way to do it is very simple. We go back to the defining equations. And what we do is we simply add and subtract these two equations. So t prime plus x prime is equal to gamma 1 minus v, you can check the algebra, times t plus x. And this, substituting in gamma there and doing trivial algebra, is equal to 1 minus v over 1 plus v t plus x. And we're going to define this as e to the minus phi t plus x. So e to the phi is defined to be square root 1 plus v over 1 minus v. And in the same way, we can show t prime minus x prime is equal to e to the phi t minus x. So these are our these are the important equations. Now, you can see immediately that, I guess I got to take away those notices. We can see immediately that t prime minus x prime, t prime squared minus x prime squared is equal to t prime minus x prime t prime plus x prime, which is equal to e to the phi t minus x e to the minus phi t plus x, which is equal to t squared minus x squared. So that's what we need for a Lorentz transformation to preserve the space-time interval between points. So we're good there. And it's easy to show that the rapidity parameters add. If we were to do something like, if we would have t comma x, I'm leaving out the y and z, they always go for a ride, under a boost with parameter phi1 goes to t prime x prime, call this b1, under a boost b2 with parameter phi2, that goes to t double prime x double prime. Then it's easy to see that t double prime minus x double prime is equal to e to the phi2 t prime minus x prime is equal to e to the phi2 e to the phi1 t minus x, which is equal to e to the phi2 plus phi1 t minus x. So that's good. And in the same way, t double prime plus x double prime is equal to e to the phi2 e to the minus phi2 plus phi1 t minus x. So we can see that the rapidity slash hyperbolic angle parameters add. So that's sort of what we wanted to show. Then finally, we have this definition for phi in terms of v. I would like to get v in terms of phi, and I'm just going to write I'm just going to show that the answer is correct rather than doing the manipulations. It would be easier just to show. Let's take the hyperbolic tangent of phi is equal to the hyperbolic sine of phi over the hyperbolic cosine of phi, which is equal to e to the phi minus e to the minus phi, e to the phi plus e to the minus phi. Now multiply numerator and denominator by e to the phi. This will get rid of the square roots before we substitute. Now this is equal to e to the phi squared minus 1, e to the phi squared plus 1. And now we substitute that previous equation. And this is just 1 plus v minus 1 minus v divided by 1 plus v plus 1 minus v, which is equal to v. So we end up getting the very important equation, v equal hyperbolic tangent of phi. And that finishes what I wanted to say about the rapidity parameter. Now I want to do uniformly accelerated motion. Which is also called hyperbolic. It seems we're always getting hyperbolic in special relativity. But here we'll see at the end really why it's called hyperbolic motion. So let's define, there's various ways you can proceed here as well. You could proceed by brute force, which is sort of what Rindler does, or you can proceed in a more elegant covariant manner using 4 vectors, which is the way I first learned it I first learned this in Meisner, Thorne, and Wheeler's telephone book. On gravitation. Sometimes it works and sometimes it doesn't. And I think I have it somewhere. I will show it. A copy from like 40 years ago. Still in good shape. Very thick book, as you can see. Okay. So let's start with some definitions. Let's start with the 4 velocity. Usually the symbol u is used for 4 velocity, not v. V will be used for 3 velocities. So we'll have u alpha, which is defined as dx alpha d tau. Tau is proper time. Alpha goes from 0 to 3. Space 1, 2, 3, x, y, z, time 0. And if I were to write its components out and sort of bastardize the covariant notation, it would be something like 1 comma vx comma vy comma vz. And here we would define like vx equal dx dt. These are the components of the velocity, dy dt for vy, and dz dt for Vz. These are not covariant because we have, well, we have t. I mean, we don't have tau. Okay, so, and then we have the 4 acceleration, which is defined as you would expect. A alpha is d u alpha d tau, and I'll leave it like that for now. By the way, I said MTW. Look at section 6.2. Okay. Now, there's a concept of the rest frame of the accelerated particle. So think of a particle accelerating in one dimension. Doesn't have to be one dimension, but you can think of it that way. And as it's accelerating, you could imagine an observer moving alongside of him, traveling at the same velocity that he's traveling always. So for that observer, the particle is at rest. Now the problem is the observer, in order to keep up with the particle, has to accelerate, so that's not an inertial reference frame. But think of an inertial reference frame moving at the same velocity as the particle, and then just stick with that reference frame. That's called a co-moving reference frame, but it's going to change from time to time. But it's inertial. We don't really need to make much use of that, but in this co-moving rest frame, the 4 velocity is a very simple form. You know, since the particle's at rest, all its components of the velocity are 0 in that frame, and therefore, dt and d tau, since they're moving at the same velocity, are the same. And likewise, the acceleration has components where the vector a, which has components ax, ay, az, is often referred to as the proper acceleration. It's the acceleration that you would feel, you know, if you were uniformly accelerating, or let's say you weren't uniformly accelerating, but at a given instant of time you would feel a certain acceleration. That's the proper acceleration for somebody who's moving at 0 velocity with respect to you. In other words, for somebody right at your position. Now let's go back to just covariant descriptions. We have u alpha, and remember we're always using the summation convention. This is equal to, just from our definition of u alpha, if we use this form over here, we can see we're going to have gamma squared, and then we're going to have the magnitude of this 4 vector. I'm going to use the 1, 1, 1. I'm sorry, the 1, minus 1, minus 1, minus 1 metric. Being a little inconsistent here, but since Suneka uses the other metric, but I prefer this metric. So it's gamma squared, and then it's going to be 1 minus Vx squared minus Vy squared minus Vz squared. Or it's equal to gamma squared 1 minus V squared. Remembering the definition of gamma squared, it's just equal to 1. So the 4 velocity always has magnitude 1. If you're using the other metric, it would have magnitude minus 1. That's one of the reasons why I prefer this metric. And that leads to a nice equation. Because if we take the derivative with respect to proper time of u alpha, we're going to get du alpha d tau times u alpha plus u alpha du alpha d tau. And we can move this one up, and we can use this one up and this one down, and they just become the same thing. And has to be equal to 0 because u alpha is a constant, which is 1. So we've established that the fore velocity u alpha du alpha d tau is equal to 0 is equal to u alpha a alpha. The fore velocity is orthogonal to the fore acceleration. It's a very important equation. And setting this equal to u alpha, that's another very important equation. And we're going to need one more equation to solve this thing. And the equation that we haven't used so far is that the fore acceleration is constant. So a alpha is equal to it's 0. It's minus ax squared minus ay squared minus az squared. Or in other words, it's minus the absolute value of a squared. I'm going to call that, just to not use the symbol a, I'm going to call that minus g squared. Think of g as the acceleration, we have from gravity. I'm going to call this minus g squared. And we're going to have acceleration, constant acceleration along the x-axis. And when I mean constant acceleration, I mean the fore acceleration is constant along the x-axis, or the proper acceleration is constant. So this gives us one more equation. Since we're only working along the x direction, a is going to have components, a0, a1, y and z are going to be 0. Okay, so a alpha is simply that a0 squared minus a1 squared is equal to minus g squared. So these are our three equations, 1, 2, and 3. And with those three equations, we can solve the problem. So let's proceed. I'm going to write down initial conditions. And I'm going to choose some that seem a little bit artificial, but actually just make it easier to plot. So at time t equals 0 is when we're going to start the clock, and proper time is equal to 0. And t equals 0, tau is equal to 0. X is equal to 1 over g. We'll see how that works out later. And dx d tau is equal to 0. So it's at rest. So at time t equals 0, it's at rest in our coordinate system at coordinate 1 over g, and then it starts accelerating uniformly. Those are our initial conditions. Okay, now let's solve the problem. u alpha equal 1 implies u0 squared minus u1 squared equal 1. And that I'll need a little later in the form u0 over u1 squared. I'm dividing by u1 squared. That gives me a 1 here, and then I'm transposing it to the other side. 1 plus 1 over u1 squared. Okay. Now my next equation is u alpha a alpha equals 0. That implies u0 a0 minus u1 a1 equals 0. Okay. And then I have a alpha equal minus g squared. This implies a0 squared minus a1 squared equal minus g squared. Now this implies that a0 squared minus using this equation implies that a1 equal u0 over u0 over u1 a0. So I have, since I'm squaring a1 squared, I'm going to have u0 over u1 squared times a0 squared equal minus g squared. Okay. Now I'm going to substitute in this thing here. So I have a0 squared minus 1 plus 1 over u1 squared times a0 squared. And this is equal to, we have a0 squared and we're subtracting off a0 squared. So it's equal to minus a0 squared, should be a u1 there, over u1 squared. And this is equal to minus g squared. So we get our first equation, which is basically a0 equal to g u1. Yeah, it's obvious which sign to take for the square roots. Everything's moving to the right. So, g is positive, so let's not worry about that. Now, let's go back to the equation. We have a1 is equal to u0 over u1 a0, which is equal to u0 over u1 and now we have a0 from there, so we'll substitute that in there. The u1's cancel, so this is equal to g u0. So this is our second very important equation. Okay. Now, let's just substitute into this equation. Remember the definition of a0 is just, I have it down. For the zeros, it doesn't matter whether I write them up or down because I'm using the 1 minus 1 minus 1 minus 1 metric. So I have d u0 d tau equal g u1. And this implies that if I take another derivative here, I'm going to get d2u0 d tau 2 is equal to g du1 d tau, and that's equal to g a1 by definition again. And we have our equation for a1, which is gu0, so now we get g squared u0. So our differential equation is d2 u0 d tau 2 equal g squared u0. Now this is a very simple differential equation. You can solve it with exponentials. It's easy if we go directly with the hyperbolic. We'll solve with the initial conditions. So this implies, when you solve this, this implies u0 equal hyperbolic cosine g tau. Let's make sure we solve all of our initial conditions. When tau equals 0, this is 1, so u0 equal 1, which is the fall velocity starts out at 1, so that's correct. The 0 component of the fall velocity is 1. I think, yeah, 1, 0, 0, 0. Need these initial. You know what? So this is good. And then we need to, if we take the derivative of this for the acceleration, we would want the acceleration, the 0 component, to be 0 at time equals 0, and we're going to get a hyperbolic sign here, and that will work out. So this will satisfy our initial conditions. And then now we substitute in here. u0 by definition is dt d tau is equal to hyperbolic cosine g tau. That implies t, it's just straightforward integration, t equal 1 over g hyperbolic sine g tau. Okay, so again, when tau equals 0, t equals 0, so there's no other constants and everything's good. Okay, so now that's one of our solutions. We're going to solve this parametrically, t and x in terms of tau, also using the parameter g. Okay, we also have, remember earlier, we have a0 equal gu1. We go back right there, a0 equal gu1. So we write u1, we know, is by definition dx d tau is equal to a0 over g is equal to 1 over g du0 d tau. We have that already up here, right over here. u0 is so we just differentiate this. The u0 d tau, a g comes out, which cancels that, and so we're simply going to get hyperbolic sine g tau. Okay, so now we'll integrate this. So that tells me that x is equal to 1 over g hyperbolic cosine g tau. And let's check again the constants. At tau equals 0, hyperbolic cosine is 1, and it's 1 over g. That's why it shows x equal 1 over g. Otherwise, I got to put a constant in here. So let me write, this is our solution basically, x and t. And now we can simply write, x squared minus t squared is equal to 1 over g squared hyperbolic cosine squared g tau minus hyperbolic sine squared g g tau. If you remember your hyperbolic identities, this is equal to 1. So this is just equal to 1 over g squared. So this is the equation of a hyperbola in xt space. And if we were to graph it, xt, if we were to graph this hyperbola, we'd find that when x and t become large, this is insignificant, so basically x is equal to plus or minus t. So these are the asymptotes. And this is the hyperbola. Over here, this point is x equal 1 over g. And basically, although we said it started at tau t equals 0, we could extend it, and it goes off. So the interesting thing about this is that if you're here and at t equals 0 you let a photon go, it will travel here and eventually it will hit the it will catch up to the particle. But if you're here, you're never going to catch that particle. So even though the particle is always traveling at the speed less than the speed of light, and the photon is traveling at the speed of light, this particle can outrun a photon. I always thought that was very interesting. So with that, I'll end this video. Again, my major concern for this is it's sort of a test. I've got a few other things I want to discuss on special relativity. I'd like to talk about the Thomas precession, the Lorentz transformation for a general velocity, and I'd like to talk about the factor theorem, where every Lorentz transformation can be written as a product of a boost and a rotation. So I'll end this video here, and then I'll take up those subjects next. But please give me any feedback you have on which type of format you prefer. Thank you very much. I'll see you next time.